Well, hello everyone. I'm Yuanjie too. You can also call me Tukey. And I'm a well-then PhD candidate at UW Transportation Engineering. But you can actually, I just passed my defense last week. Well, thank you. So my work, dissertation work, is on how to model ride-hailing like Uber and Lyft driver behaviors and how to nudge like their behaviors, like accepting trip requests or like making their work choices into like more sustainable directions. But this one is kind of my ongoing little project. It's leverage deep learning in electric vehicle charging demand prediction. So I'm very happy to share my work and see like if you guys have suggestions. So okay, let's get started. So why do we even care about electric vehicle charging demand? So have you noticed that there are more and more electric vehicles on the road recently? You probably have noticed like a Tesla on the way to the conference today. So yes, there are like increasingly more people choose to adopt EVs recently, and also in fact in 2030, according to a CNBC report, there will be like half of the new cars sold in the US would be electric vehicles, which is fantastic. But just imagine that all these EVs will be need to be charged in the EV charging stations to like ensure their functioning. So that would actually impose a great challenge on our power grid. So to ensure that our EVs have a good experience, running around without worrying about running out of electricity, and also to help with the stability and sustainability of our power grid, it is essential for us to be able to predict and understand what are the charging demand of those electric vehicle charging stations. So that's why we care about this question. And so here comes to our research question: how do we predict EV charging demand by leveraging deep learning methods? So here, when we talk about EV charging demand, we define it as the energy consumption of a specific charging station on a daily basis. So basically, we're predicting the energy consumption of a charging station tomorrow. So that is our research question. And the data we're using is the EV charging station usage open data, and that data set is provided by the city of Palo Alto, California, and that data set spans from July 2011 to December 2020, and it contains information on charging station locations and the type of the charging connections available, and each charging session duration, starting time, ending time, and also the energy consumption, etc. I can show you the data set if you're interested later. When we go to the methodology part, so our dependent variable is the daily energy consumption of every EV charging station, and we use some baseline models as well as some deep learning models. So the baseline models we're using include the 90 forecast, which is just using a previous value to predict the value tomorrow without doing any change. And we also have the average forecast, including the mean and median. So basically, the average forecast means that you calculate some statistics like the mean or median using a series of the past values to predict the value tomorrow. And our deep learning models, we're using an MLP, that's a multiple layer perceptron. That's, as you guys probably already know, that's a classic neural network with multiple layers of fully connected nodes. And then we use convolutional neural network, which is very good at recognizing the patterns in the data set, and which is also commonly used in time series modeling. And we also use long short-term memory network, LSTM. So that one is is a modification of the recurrent neural network, and which is designed to capture to do the time series modeling. And then we also have two hybrid model here, which is the similar concept of combination of CNN and LSTM, but their structure is a little bit different. So the CNN LSTM is kind of like a sequential model. First, we use CNN to capture the patterns in the data set, and then we use the LSTM to capture do the time series modeling. And the LSTM is basically, we incorporate the convolutional convolution operations inside of LSTM cell. So we can come back to the details later if you guys have questions. So okay, so let's quickly look at the results. So before we go into the modeling part, it's essential for us to look at some data descriptions. So that helps us to really understand what the data looks like, and also to helps us maybe to define the model structure. So here, if we look at the EV charging station locations first, we can see that in 2011, and we can see that there are 5 charging stations here, and all in Palo Alto downtown area. And this is Stanford, this is like the downtown area. And as the time goes, we can see, oops, there are some new charging stations showing on the south. And then it's more and more, it becomes more and more and more. And until 2020, here we can see that there are 47 EV charging stations in 2020 based on the data set we're using. Of course, yesterday when I was scanning online, I found Palo Alto now in 2024 have 354 charging stations. Well then, I look forward to using their data set if that's open to the public. So that's the spatial distribution of the EV charging stations. Now let's look at the temporal characteristics of the charging stations. So basically, this visualization, the horizontal axis is the years, and the vertical axis is the energy consumption. Well, we can also see other metrics, but here our focus is the energy. And we can see that, so basically this visualization shows the monthly change of the energy consumption of every charging station, and the red line is the average of all charging stations, and the blue line is if we move around our cursor, we can see different charging station trend. So here, what we kind of want to see is whether there's a seasonal pattern or a monthly pattern on the data set, because deep learning models are especially good when there are some internal patterns there. But interestingly, we didn't really find any monthly or seasonal patterns. But there are interesting things. We find that actually there are in 2017 and 2020, there are 2 energy drops here. If we look at if we look at the data aggregated to the year, we can clearly see 2 drops in 2017 and 2020. We actually are very curious why this is the case, and we tried to find information online but couldn't really find any. So if you guys know any information, you're welcome to tell me, and I would really appreciate that. So that's basically the trend of the EV demand over the years. And we also want to see whether there is some trend weekly patterns or daily patterns. So here, this visualization shows the daily pattern, weekly pattern, and monthly pattern of the data set. So if we look at the daily pattern, and if we go across different years, we can see that, well, one obvious pattern is before, in the early mornings, before 5 a.m., or in the late night, after 22, after 10 p.m., the charging demand is lower. But except for that, there isn't really an hourly pattern here. Every charging station seems quite different. Even if we look at different years, it's quite different. So if we look at the weekly pattern, well, this visualization has a little bit of glitch. It needs to be shift a little bit to the right. So we can see that during the weekdays, the charging demand is relatively higher compared to in the weekend. So this could be something interesting here. And monthly, that's quite similar to the previous visualization. We can see that there isn't really a monthly pattern or seasonal pattern here, except for we can see a huge drop in 2017 and 2020. There is a huge energy drop here. So, well, yeah. Do you have COVID? Oh, maybe. Yeah, 2020. Yeah, and 2017. Yeah, that's a really interesting. insight, and I'm also wondering about like 2017, like what exactly is the reason?
Oh, yeah.
Oh,
Or were more stations coming online in those years? So like there's an average drop because now you have more stations.
yeah, that's a great point. So for that case, if we really look at this, it's pretty clear to look at this. So here, if we look at 2014, that's the exact case that you're mentioning. So it's like we can see there are more stations coming up. You can see like here it's like these stations coming up, so that, and then that charging demand of those new stations is not like coming high enough so that there is a visible like average drop. But that average drop is kind of like fake. So yeah. But in the later years, if we see like in 2017 and 2020, that seems to be like, if we look at, we can look at this more clearly in here. Yeah, we can see all those different stations, not only the average one, but all those individual stations are like dropping. So if we see like this is 2017 also, maybe there is a huge event like that caused this. But thank you for the insight. It's really, really helpful. So, okay, so these are the descriptive analysis. Let's look at our preliminary modeling results. So let's first look at our performance metrics. We use mean square error, mean absolute error, and root mean square error, like 3 performance metrics to see like how the model is performing. And so this box plot come from, we run the models for like 30 times repeatedly, and then we come up with a distribution of like each model. And the horizontal axis is the different models, and the vertical one is the performance metrics values. So if that's a good model, we want the mean value to be low because we want the error to be low, and also we want the distribution to be like narrower. So here we can see that the comp LSTM has the best performance by having the lowest performance metric like MAE, and followed by LSTM, followed by CNN. And this discovery is persistent if we see like different performance metrics. This is quite persistent across different metrics. So that is our performance metrics. And I also plotted out the loss function of every model. They all seem pretty normal here, like the loss function change. So I'll skip this. And we also plotted the comparison between the real data versus the prediction over time. So basically, if we look at these, so these are different models, and the red line is the predicted value, and the gray line is the real data. And what we can see is the prediction, the deep learning models like LSTM and conv LSTM can capture like the little, like the trend. If the data is going down or up, it does capture that, but it cannot really capture like the lower values and the higher values in a data set. Maybe it does have some pretty like outliers. So that's our observation, and we can observe the same thing by looking at the difference chart. So I'll skip this part. And also, to further observe this problem, we plotted the real data versus the prediction data correlation here. So we can see the horizontal here is the real data, while the vertical axis is the predicted values. So basically, if that's a good model, we want the values to be like near the diagonal line. So, but we can see, for example, like at the LSTM model, we can see it's kind of underestimating, it's overestimating the lower values and also underestimating the very high values. So that's what we're gonna solve in the next step. So that's our preliminary results. It's ongoing, and the current conclusions are, so first we investigated the charging demand of the EV stations in Colorado from 2011 to 2020, and we found there are some daily patterns, weekly patterns, but there isn't really a monthly pattern except for like 2 energy drops, major energy demand drops. And in terms of our model, we adopted 3 baseline models and 5 deep learning models, and the results show that the conv LSTM model has the best performance, followed by LSTM and CNN. And the result is persistent across like different performance metrics. And all 5 deep learning methods tend to underestimate the higher energy demand and overestimate the lower energy demand. So that's our current conclusions. But then in the future research, we are actually so now we're actually doing the univariate prediction. So in the future, we're gonna incorporate more variables to make improve the model, and also to consider the spatial relationships between the charging stations. So we're thinking about maybe using graph neural network and do hyperparameter tuning. So that's the current state of the little project. And thank you for listening. I would really welcome if you have some questions and suggestions. Thank you. Oh, go ahead first.
You, we're treating all of the EV charging stations equally. Like, can you treat them, or did you try to treat them as like, this is a Tesla charger, or this is a more general charger, or this is a charger in a hotel, or this is a business, or anything like that?
Oh yeah, that's a great question. So basically what we're doing is we are predicting different, the different charging stations as an individual charging station. So sorry, I forgot to mention this. So basically for the result part, we only presented this one, like the charging station on the Hamilton Avenue as an example. But we are predicting them differently and maybe to incorporate them together. Yeah, so, go ahead.
I was wondering, do you have data on downtime, like if it's out of order or something like that?
You mean downtime? Can you be more specific?
It's broken.
I don't really have that data, but I wish I do. Yeah. Yeah. So I'll come back to you, but that's a really great question. So you were saying?
Hi, great talk, thank you. I had a question about what's the granularity of your time series data? Is it just hourly or 15-minute?
Oh yeah, I can show. So basically, the data set itself is basically individual data of each charging. So let me show you. So this is the original data set. I did a little bit of a variable selection here, but that's the original one. So basically, so each line records one charging event of a user. So basically, it's pretty fine, granular, and you can see station name and also the charging event start time, end time, and also how much energy it's using, how much gasoline it's saving. So that's the original data, and for this study, we are predicting the charging demand in an hourly basis, in a daily basis. So it's basically we're using a data set, the previous values to predict the charging demand tomorrow.
So you don't know what kind of, so you have charging events is what the data set is. Do you know what kind of car is being charged?
That we don't. Yeah.
Yeah, that would be interesting to correlate.
Yeah. But it does have some other interesting columns that we might be able to incorporate later, like the port types. But yeah, that's a really great question. Thank you.
So is this mainly a time series of the charging events, or did you also incorporate weather data at all? I think EV charging can possibly vary by weather patterns.
Yeah, that's a great question. So now this preliminary status is we only use the univariate data, which means we just use the one time series data, but we're going to incorporate more to make it a multivariate model. Yeah, that's the next step.
Thank you for a great talk. I have 2 questions. One, since you have it at this hourly level, have you considered doing the prediction at the hourly level to kind of get rid of some of those spikes that are happening at the daily level and then re-aggregating back up to the daily level?
Oh yeah, that would be a great idea. I would certainly try that, but the model is currently very slow, so I think
that was my second question. Was the neural networks are pretty computationally expensive. I'm curious where your threshold is of honestly, the mean and the median were better than some of the neural networks and are computationally much more efficient. Like, I know as a thought experiment doing the neural networks kind of expands on that, but where do you draw the line of honestly the mean is good enough
Well,
in
yeah.
a business context?
That's an amazing question. So honestly, when I was looking at the like this box plot, I was like, actually the mean is good enough actually. But I mean that's a good starting point for me. And then if we incorporate more variables and also if we consider the spatial interactions between the stations, it might have like much better performance. So that's like the next step. So yeah, I agree with you.
I have another question on this one. You mentioned grid applications for this. Are there other applications you had in mind for, some others? Curious what the goal
Oh, yeah.
applications was.
Yeah, that's also a great question. So the application for that one, so mainly I was doing this because if there are more and more EVs on the road, and then like they could actually pose pretty good, like great pressure on the power grid. So if we could like understand, like we could predict the demand tomorrow or like next hour, then we could like make the power grid smarter and they could adjust it so won't like lead to power overload or like outages. So that's the main application that we're thinking about. But do you have ideas about what else, like what other applications that could be used?
Well, I'm wondering, there are some kind of newer applications for EVs, the dual charging, right, like where the EV is doing the demand response or frequency regulation for the grid. That's a great idea. Like the other thing I was thinking is maybe like can regulate like how to encourage the users to charge their vehicles in different times and then to optimize the energy using. Yeah. Thank you.
Kind of going off of that, I'm curious if you have any information about like home charging data in the similar area, so that you can sort of triangulate findings between that and then public charging and come up with recommendations of how to interact with it.
Yeah, that's if we have that data, that's great. So the other thing I was thinking is the home charging. Usually people charge it like at night when people like go to sleep. So that actually doesn't really impact the power grid that much because not much demand was happening at that time. But surely that would help if we do have that data set. So I'll like search in the future and see if there are any. Do you have suggestions?
I was just thinking because like people charge at home, but they also charge at work, so there are big interactions and how that might affect different parts of the grid in that specific location.
Right.
I don't know.
Yeah, that would be really interesting if we could look at the charging behaviors and then do the recommendations like in time. That would be something really cool.
We'll take one last question for this topic.
Okay, so we can talk later about like
Yeah.
Okay.
Go ahead.
So I work at an electric company and provide residential charging. So
Wow.
yeah, we definitely, this would be, have you thought about like working with an electric company to use this model for their residential prediction? Because we find that that's the largest energy draw rather than public charging stations. Like we would be interested in this information
Wow.
for residential customers.
Wow, that would be super cool. I would love that. So I'll be exploring this like kind of like as my personal like hobby project, but I would definitely love to like to talk with people who are experts on this and see how we can improve it and put this into real use. Yeah, thank you. I'll definitely harass you after this.